Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Okay, so welcome everyone. Thanks for tuning in. My name is Francois Barthelat. I'm a professor in mechanical engineering at the University of Colorado Boulder. And my research is at the intersection between mechanical engineering and materials. So more specifically, I develop materials which are inspired by nature. So I did my PhD, for example, on the strength and toughness of seashells, and tried to discover new micromechanisms of deformation and fracture that are not necessarily observed in or exploited in engineering materials, and then hopefully understand this to an extent that we can go to the lab and in the second stage make engineering materials that are inspired by the seashells. So we did seashells, we worked on fish scales, fish fins, we did a bit of bone biomechanics and bone-like inspired biomaterials. And then more recently, so far it's been very much about strength and toughness. And I would say that recently we've been interested in morphing materials that are materials that change the geometrical shape from external stimuli. And so that's what took us to fish fins. So that was our latest work.
Yeah. First of all, I'm a fan of your work because I think designing tougher material, I think that's something I think most in the community, and I think generally speaking, we need tougher material. But let me ask you first about how nature, for example, you mentioned seashell, for example, and there's a lot of example of animals, they have this kind of toughness and tough structure so that they can resist to damage or to protect themselves. If you could tell us more about the examples, how they manage to this evolution, how it happened this creature can manage to have this kind of tougher material or structure to protect themselves.
Okay, yeah, that's a great question. Yeah, so the first of all, I should say all these materials we've been looking at they have a high content of mineral, which makes them stiff and hard. So you get the stiffness, the hardness, that's the easy part. Now, typically, when you make something highly mineralized, they tend to be more brittle. So that means they crack more easily. If you take a piece of skin, for example, or a piece of rubber, then it's inherently a tough material because it deforms rather than fracturing. But then if you remove this kind of large deformation capability by putting a lot of minerals, then you get brittleness usually. So the extreme example is glass, right? So glass is it's pretty stiff, pretty hard, but then it doesn't resist crack propagation. So it's not a very tough material, and then it doesn't resist impact because of the same reason. So the secret really in nature, and that's quite interesting, that we found this kind of general rule that you will find in seashells, in teeth, in bone, in fish scales, is that we have essentially building blocks, which are the mineral part of the material, and these building blocks are joined by weak interfaces. Okay, so when I say weak interfaces, these are kind of lines within the material or planes within the material where cracks can propagate more easily. Okay, and so that's very important because so it's first of all it's a bit counterintuitive, right? Because nature makes actually better material by putting a lot of weak interfaces within the material itself, which sounds counterintuitive, but in terms of crack propagation, it makes a lot of sense because with weak interface, you gain the capability to control where the crack is going within the material. So for example, if a crack is propagating this way, because if you stress the material horizontally, let's say, the cracks will tend to propagate vertically, right, across the direction of pulling, and then in a material like glass, the crack will go straight without any reason to deflect. Okay. Now, if you put a weak interface across the crack propagation, the interface is weak enough, then you may convince the crack to deflect into this interface, right? And so already you manage to control to some extent crack propagation. And so nature is really master at doing this by using all kind of 2D and 3D intricate architectures and networks of this weak interface to actually deflect cracks or divide crack into two sub cracks, or trigger all kind of mechanisms. And so that's the if you look at how the bone or teeth or seashells or fish scale fractures, you will find that all these mechanisms are based on this idea of like hard building blocks joined by weak interface.
Yeah, wonderful. Maybe I guess ask you about this kind of interplay between the hard interface and weak ones. What kind of morphology do you think? Is it something, do you believe that's how they represented, or the way, because when we see the examples, it's different. For example, you did the inspired glove that minimized the injury in workplace and based on fish skills. So how do you see this morphology play the role here? What's really other element you think is still not answered? Maybe morphology, I don't know. What do you think about that?
Right, yeah, so it's a very interesting question because in nature and in the materials that we develop, there's no like one size fits all kind of design solution that will that's kind of magical and will work for any kind of application. Okay, what we find is that depending on whether you try to develop a material that resists cutting, for example, or sharp puncture, like a protective material, or maybe you want to develop a material that's very strong when you try to flex it, you will find that the type of architecture and that's perfect for each of these applications may be quite different actually, right? So this is very much application dependent, and it depends on how you stress how you load the component mechanically, right? That being said, there are some kind of universal patterns that are found in these natural materials, and one of them is a brick wall, essentially structure where you just like a brick wall. So you have the hard blocks are like the bricks, and then the weak interfaces are the mortar essentially of the bricks, right?
Yeah.
The adhesives of the bricks. And then if you look, it's quite interesting because if you look at a house, for example, so I spent about 13 years in Montreal actually before moving to Colorado, and there's a lot of old houses, brick wall houses, and sometimes you can see cracks that propagate maybe from the corner of a window, and the crack is being deflected by the mortar, right? So we find this type of a lot of the same mechanics actually in brick wall. So this structure of brick wall is actually, you can find in many seashells use that trick. So they make literally like 2D or 3D microscopic brick walls where you have some mineral plates or tablets which are basically attached by proteins, by bioadhesives, and that's at the microscopic scale. In bone, if you go down to the nanoscopic scale now, very small, and you're going to find the same kind of the structure actually, some kind of nanoscopic tablets of minerals that are arranged in almost like a brick wall. And you also find this in teeth. We also find this in fish scales, and so a different length scale, but it seems to be an excellent recipe to make materials that are very strong, stiff, and also tough in tension, right? Yeah. And so it's quite fascinating to find that in materials that are taken from animals, which are completely different, right? On the evolutionary tree, there are totally different families of materials. You find that somehow nature converged to the same general solution to solve the similar mechanical problems, right?
Very fascinating. So I'm curious to ask you, when you have this kind of, you look to what already we have in nature and you try to design this kind of different category, completely different material to make this desired goal either be tough, lighter, smart, as you mentioned, it depends. How you rearrange this material? I don't know what's the strategy. Do you have to take exactly how already evolution designed this in a certain way, or do you think you have to tweak it in a certain way? I don't know how this transition is going. It's kind of course we speak about inspiration or just like biomimicry, but I'm curious in material design, because is it the same arrangement, how you arrange them, or how to do something different?
Yeah, it's a great question. Yeah, it's a great question. So we do a lot of tweaking, actually. We do even more than tweaking. The materials we make inspired from the seashell, for example, they look totally different. They don't look like a seashell at all, actually. I would have to tell you this is inspired from a seashell, so you can, right, and show you how, but it's not obvious, right? And so the key idea is that we don't copy directly in nature. We don't copy directly these things, these great materials we find in nature. So that's why we prefer the term bioinspiration over terms like biomimetics or biomimicry, which imply that you simply copy what you see in nature, right? And people have taken that route in the past, and sometimes it didn't end very well. I'm thinking of this engineer girl who Bonnie was the name of the engineer. So he developed an airplane in the early 20th century, and he was convinced that the best way to make an airplane was simply to flap the wings, right? But he didn't have, he was simply copying birds, but he didn't have a deep understanding of aerodynamics, and so that ended up in a disaster. He actually died in his plane, basically. It didn't work at all, right? So shallow copying of nature doesn't work. It's not a good route. A term we prefer is bioinspiration, where we really work hard in the first phase of the project as understanding the natural model. So do a lot of mechanical tests, mechanical modeling. So we really understand what makes this natural material so good at what it does. So we can abstract this key idea, or sometimes it's only one idea, sometimes it's a combination of maybe 2 or 3 ideas into our engineering system, right? So I mentioned this general rule of using hard bricks bonded by softer, weaker interfaces. And so we actually use this concept, this idea, for example, to develop bio-inspired glasses, right? So glass panels that have the same kind of architecture. So obviously the base material for the bricks is different, right? It's not calcium carbonate, which is actually a pretty poor ceramic, but that's all the seashell gets from the seawater, right? As engineers, we can use better base materials. And also we don't work at the same length scale. So the bricks in the seashell may be microscopic in size. Our bricks are more in the millimeter in size. So when you take all this into consideration, we kind of abstract the brick wall, we abstract the weak interface, but then the end result is some kind of glass panel, and it doesn't look anything like a seashell, basically, right? Okay.
Great. So, yeah, I'm going to ask you in that case, do you think when we aspire to design tough material, do you think we can push the capabilities to have material with tough properties, I don't know, maybe beyond what we have in nature, and maybe never damage? I don't know, that's the dream. Everyone designs something very strong, never damaged. I don't know, do you think we can achieve that goal, that have material never damaged, or that doesn't make sense?
Yeah, so so I think this, I'm trying to think of where to start with to answer your question, but the idea of damage is a bit tricky, because if you look in the recent history, for example, of how to make strong ceramics, okay, so ceramics it's a big area of research, how to make. So ceramics, of course, they're very stiff. I'm talking about engineering ceramics, like boron carbide, aluminum oxide. These are very stiff and very strong, but they tend to be brittle, right? And so they're very sensitive to damage, essentially. So if you have a little impact on the surface of a ceramic part, then you have to change the whole thing, because that really decreases the strength. Just like on your windshield, if you have a little impact on your windshield, it's highly recommended that you either fix it or you change the windshield, because the overall strength of your windshield is compromised by the presence of a small defect, right? So there's 2 routes to address this. And so historically in ceramics engineering, one way is to try to suppress the defects completely at fabrication stage, which is quite expensive to do. Another route that to me it's a bit more interesting is to say, okay, there's going to be defects. There's going to be either at the fabrication stage or when you use the component, there's going to be defect. Now, how can we program some kind of mechanism within the material so that the cracks that will want to grow from these defects will be neutralized? Okay. And so nature actually uses the second route, because if you look at your bones, your teeth, seashells, that contain tons of defects. Actually, okay, so the idea is not so much to prevent the formation of damage, which is extremely difficult. Damage or initial defects are already there, but how to design your material, to create your material so that these defects don't compromise the overall performance of your component. Okay. So that, I think that's the vision there. Okay. Now, can we ever make a material that never breaks? I don't think this will ever happen, right? All we can hope for is to increase the strength, but at the end, there's some limitation. If you take two atoms of material, right? You pull them, you look at the strength is extremely high, but you can never, theoretically, you can never exceed the strength of the interatomic bond between two atoms, right? So there's only that far you can go with this, but I think there's still a lot of room for improvement, right? For many materials like glasses or ceramics, they make them stronger or more damage tolerant. Then there's still a lot of work to do, and nature has still a lot to teach us in these areas.
Great, yeah. And I curious to ask you about the redundancy in that case, because I was looking, for example, spider, when they build their web, and if there's damage happening in a certain part of the web, it's still, have the whole structure. I don't know, how do you see that also if you apply this tough material? Do you think the redundancy, if that you can have this kind of, I don't know, do you think the concept of redundancy can be applied in designing tough material? Or maybe do you think there's something in evolution is not perfect? You think we can engineer something better than what we have already in evolution? This is maybe missing.
Yeah. I mean, there's different questions in your question, I think there, but I mean, the case of spider silk, you do see redundancy, or I guess you could call it again damage tolerance, right? The fact that the whole spider web is not, if you break a few strands in the web, right, the strength of the web and the functionality of the web is not compromised, essentially, until you really put a lot of damage into it, right? Now, can we are these materials we see in nature perfect in the way they constructed? Probably not, right? There's because there's lots of constraints. For evolution is still going on, right? Anyways, these are not these materials keep evolving, and then there's a lot of constraints in nature that we don't have as engineers, right? So nature has to grow things at room temperature, more or less, right, at normal pressures, with very limited very limited number of types of raw materials, right? In nature, nature only, at least for structural components, there's only a few atoms that are really used in nature, right? So as engineers, we have access to the full table of elements, right, so that we can use to actually enrich the chemistry of these materials, and so we can actually go beyond some of the limitations that are set on these biological materials. Right? I've been to conferences, in biology conferences, zoology conferences, and zoologists and biologists, they hate the term optimized, right? At some point when I started in this area, I said, okay, we have this great material in nature, it's been there for millions of years, hundreds of millions of years, it's probably optimized, but it's not. In nature, things keep evolving, and sometimes optimization implies that you have a global minimum. Sometimes you have some construction in nature that are stuck in local minima, and so it's a very tricky question.
Yeah, that's interesting. Yeah, but I'm curious to ask you and your group about maybe the challenges, and maybe it's still a question for you in the research. You're saying it's a hard question, and you don't know the answer for this question. I don't know what kind of challenges you still have, or hard question you don't know the answer for when it comes to your research.
I would say hard, difficult challenges we're working on in our lab. And they're not necessarily about looking at biological materials per se. although there's quite a bit of challenge sometimes to trying to understand these materials because they're quite complex and there's a lot of layers of complications in terms of structure, etc., at multiple scales. But I think the main big challenge we face in this process of bioinspiration is fabrication. How do we fabricate materials in the lab that duplicate what we see in nature, right? So nature, these biological organisms, they really master at making nanostructures, microstructures, some of them quite, I was talking about this brick wall. If you look at a piece of seashell on the electron microscope, you're going to see this super nice, almost perfectly regular brick wall at the micro scale. And we don't know how to make this in the lab. If you look at people have been very creative over the past few decades at using all kinds of techniques like to align microscopic, platelets into matrices and to try to duplicate this type of brick walls. But if you look at the state of the art, like brick and mortar material at the micro scale, it's still it really pales in comparison to the natural model, right? So fabrication is a big challenge, right? Even if you understand how the natural system, your natural model works, and what it should be in the lab, then you're gonna hit a wall when it comes to fabrication, often because it's very difficult to duplicate biological material in the lab. I like to, when I'm asked this question, I like to use the example of Velcro. There was the Swiss engineer de Mestral who found that you have these seeds, right, with the little hooks that these burrs that basically the idea is essentially to attach to animals or to your socks when you walk in the mountains, and this way the seed can travel very far. So that's the idea. So I think it struck him that we could make a material using this hook and loop mechanism, right? But then it took him 10 years to find a process to actually make this on a large scale that could be used in actual applications. And so it took actually 10 years from the time the inventor understood the hook and loop mechanism to the time that he found a way to actually fabricate Velcro, right?
Wow, that's interesting.
And that's pretty representative of what we see today in bioinspiration, right? So you understand what you want on paper, we see it at work in nature, but then when it comes to making artificial things that do the same thing in the lab, then it can be extremely challenging.
Because this cue, if we want to achieving the capability for fabrication that we have the same material as we have in seashell, what does it take to achieve that? Maybe the direction, is it the machinery, is it the approaches? Where do you think it's the right path we have to go for, or maybe the question, so that we can achieve that goal?
Yeah, that's the main bottleneck now to applications, right? How to find economically feasible approach to make this bio-inspired material on large scale, right?
Yeah.
So if you ask different researchers in this area, you may have the very different answers, right? A lot of the approaches nowadays tend to keep the same, to try to make materials at the same length scale as nature, right? So if you see a microscopic brick wall, try to make a microscopic brick wall in the lab. Our approach, but the result, the problem with this approach is that the result may be quite imperfect compared to the natural system. So you may have a pile of bricks, right, which are roughly aligned, but they're not as perfectly like brick wall like as you see in nature, right? Our approach has been to scale things up to the millimeter so that we have much better control over the architecture of the things we make in the lab. And so this has been quite successful actually, because as soon as you scale up, then you have access to many more fabrication techniques. So the brick walls we make in this glass-inspired material, for example, seashell-inspired glasses, sorry. The brick wall we make, the bricks are like millimeter in size, I would say, but the arrangement is perfectly periodic.
Great, yeah.
Yeah, which is critical, I should say, for for all these mechanisms that are so important to make the seashell so tough. They actually rely on the near perfect periodicity of the architecture. We show in a recent paper, we show that any deviation from that perfect periodicity will drop all the performance of the material. So we want to make it as periodic as possible.
Yeah. But I'm curious to ask you in the process, maybe, I don't know if you have found something maybe counterintuitive, the way the design, maybe an inspiration, but you think it was counterintuitive to the way you think about the structure, or I don't know if you have any moment that was counterintuitive or I didn't expect.
Yeah, but I think that's a great question. I mean, the very idea of putting weak interfaces within materials to make them stronger is very counterintuitive when you think about it. So when in my lab at some point we started we wanted to implement the lessons we learned from seashells into glass, and we chose glass not because of particular applications actually at the beginning, because when you learn fracture mechanics, glass is a great material. It's an example of a brittle material that doesn't resist fracture, right? So we wanted to take glass and make it tougher using lessons we learned from seashells. And then we published a paper, I think in 2015, with our results, where we actually literally took a laser and engraved. We took a piece of glass and we shot a focused laser to make many little micro cracks, like star-like micro cracks, side by side, and we actually literally engraved lines within the material. And the idea of these lines was to create weak interface to guide cracks, incoming cracks, into specific configuration, right? So the idea was to take a nice piece of, again, to take a perfectly fine piece of glass, which has no defect, and with a laser, we literally shoot defects into the material to make the material better. After we published, I talked to some people at big glass manufacturers. Some of them contacted us. Actually, they wanted to learn more about our approach. And the conversation was going well at the beginning, but as soon as I told them we're shooting a laser at glass to create defects, then I could feel they were shaking on the other side of the line, and they almost hang up immediately, because this goes completely against the philosophy of design and glass engineering, which has to do with suppress damage, make sure there's no damage inside the material or at the surface, etc. This is bad for glass. And with our approach, it's totally counterintuitive. We actually make defects within glass to create weaker lines to actually guide cracks, right? And this works great, and the nature uses it again for many in many materials, and we actually demonstrated that you can use it for glass as well.
Transition from the lab to industry, for example, the application for designing this tougher material. Do you think there's a trade-off here? How do you see this kind of applicability that can be used in industry recently? This kind of research about designing tougher material or any kind of material we want. Do you think it has a room for
I think absolutely, absolutely. I think there's tons of room, because we at the end I'm an engineer, right, by training. So I actually make things and that will hopefully end up in actual applications relatively shortly, right? So the type of materials we've been developing, we are again going back to fabrication. We always wanted to make sure that we could they would be scalable. That is, the techniques, for example, this laser technique I mentioned, it can be used to make very large volume of materials at a modest cost. So so that makes, and then of course if you can show with demonstration material that you made in the lab that you increase the toughness of glass, for example, for a cost that's quite reasonable, then that becomes immediately very attractive for industry. Okay. I don't think there's any we have to make any kind of trade-off in our thinking, in our intellectual thinking, to try to approach industries and to make them more interesting in materials, because from the beginning that's what we had in mind, right? Go in the lab, make a bio-inspired material, and actually do mechanical tests and show that it's better than what's currently on the market in terms of glass if we do glass, right? So we always compare we always compare our materials with like a reference state-of-the-art material. For example, when we worked on glass recently, we used that bio-inspired architecture to make impact-resistant glass panels, and we always compare with what's available now on the market, like tempered glass, laminated glass. So we do the test on using the same techniques on these existing materials for comparison, right? So that makes it very interesting for companies, I think, when they see that. And working with companies is quite, to us, it's been very enriching and interesting, because they always take us down to earth and say, okay, you can tell all the stories you want about weak interface and nacre and seashells, evolution, etc. At the end, they want to see that you have tempered glass, you have your glass, how much better it is. Give me the hard number, and I want to see the hard data. So it's kind of forced us to keep our feet on the ground, and then actually kept us on track to this objective of really making better engineering materials.
So since we're close to the end, I have a few questions. Maybe what is your aspiration when it comes to designing the material? For example, these properties. Do you still think there's other properties you want to add to the material? I don't know what's your aspiration when it comes to this research line.
Yeah, that's a great question, actually, because recently we started to look at other property. I'm going to start over actually on this answer. Yeah. So it's a very interesting question, and so over the past 10 years or so, we've been focusing on fracture toughness and how to make tougher glasses or ceramics. And more recently, we started to look at other properties. And this brings me to morphing, is one of these properties. That how does nature change the shape of objects and components with a minimal amount of muscle forces? And so that's what took us to fish fins recently, actually. So that's moving a bit away from strength and toughness and more about how a material can change shape very effectively in nature, and what we can learn from it to applications in robotics, for example, or aerospace.
Yeah, that's very interesting. And maybe I can ask you about the change in that case, because I think that's also very interesting topics in robotics. How you can, I don't know, manage to do that with minimum energy, or this should be change and maintaining the original properties as well.
Right. Yeah. I think it's a very interesting question, and I think that one of the things we're very excited about actually is that the solution you find in a system like fish fins, which are extremely efficient morphing material, is pretty similar to what we found in seashells and bone. And again, you find this idea of hard building blocks, which have a finite size, not too big, and they are arranged in specific architecture, and they attach together by much softer, much more deformable proteins. And so you find again this same idea of very hard combined with very soft in intricate architectures to generate some very unique and exciting functionalities. So that's what I think that's the general theme of our research, is basically this, right? Very hard, very soft architecture, weak interface, and see in nature, how does nature start with this and plays the game and generates all kind of interesting properties and functions.
Yeah, great. So a few questions left. Maybe the first one about optimization, because you mentioned at the beginning that, for example, in zoology, they hate this word of optimization, if I understood correctly. And for you, how do you see these tools we recently have to design this interfaces, like our multi-material? How do you see the tool? Do you think there's something need to be considered, or how do you think about the current tools we have?
Well, there's I would we do a bit of optimization in our research, but it's very crude. So the main methods we've been using actually is it's not so-called topology optimization. What we do is more like geometrical optimization, and our approach has been to take to develop relatively simple models either like small, like closed form solution or simple theoretical models, or to use computer models, but they're very inexpensive to try to capture the mechanism. And then computationally, all these models, they are taken individually, they are extremely efficient. So that means you can run hundreds or thousands or millions of them overnight, for example. Okay, so once you have this in head, you can actually do all kind of parametric study and look at the effect of geometrical change on material response or mechanical performance. And so that's our approach to optimization has been precisely that, right? Instead of trying to look for the design space and using optimization, like complex optimization tools to find the best design, we just explore the entire space. So this is called brute force optimization. You just take we make the design space small enough, and our models are inexpensive enough that we can just try any combination. Yeah. And now it's not very popular with people doing optimization because it's not elegant at all. We just try every combination. But given the simplicity of the model, if your design space is not too big, and given the power of the computers nowadays, then that makes more and more sense, I think, this kind of approach. Yeah.
Interesting, yeah. So two questions left. The first one, I don't know if in the research do you have moment of doubt, because sometimes we have ideas, but we are not sure whether that's right idea or, it would lead to something. I don't know how you deal with doubt in research. If you have new ideas or something, do you have moment of doubt?
Yeah, sure, yeah. I mean, that's part of our job, yeah. I think with experience, you deal with the doubt in if what you're doing is going to work much better, and with experience, you're willing to take more and more risks in terms of what you're trying in the lab, which is great, I think. In our line of research, I think we have a great advantage is that we see things in nature, and we know that the performance is very high. That has been measured often before by others, and we know that it works. It's there, it's been there for hundreds of millions of years, it works. So we know there's something there that makes it so good. Now we need to find that thing, right? People who start to design new materials from scratch, they may take one direction for material design and development, but they don't know if it's going to end in some attractive properties at the end. So this is much more frightful, I think, when you don't have in our case, again, we have a natural material that we know works very well. And so we know there's something to find in this material. If you look enough with the right tool and for long enough, then you're going to find that secret. And we know it's in there.
Yeah. Great. Yeah. Finally, I don't know if you have any advice, maybe in the field or you have received and was life-changing.
You have to go out there and make mistakes, and I like to tell my students we do a lot of experiments. So I like to tell them to go in the lab and mess around and try all kinds of things for like a month.
That's great.
And then you push the limits and you make a lot of mistakes, but then you cannot make yourself comfortable in the lab. So that's the only way is to actually make all these mistakes and to mess around for.
That's very good.
Of course, don't break anything expensive in the lab, but then within these limits, of course. But I think it's something that's important, I think, at the beginning, because good students come in and they want to do everything right the first time, and they want to optimize their time in the lab, and so they think they're going to jump to perfect experiment from day one. But I think this process of messing up in the lab and try many different things on purpose almost to see push the boundaries of what's possible is very important. Another thing I would say is less is more. That is, in my experience, our own research and what I see often in our favorite papers from other groups is that the tools they use for the discovery are is quite limited, actually. There's maybe one or two techniques combined, but no more than this. And sometimes the equipment is quite inexpensive, actually. It doesn't have to be like fancy, extremely expensive microscopes to do great research. So to do great research, I think it's, if you work within the confine of some constraints in terms of the range of instruments you have at your disposal, that constraint is very critical to do good science, I think. I would hate to be in a lab where I have access to every single equipment available nowadays for experimental test or characterization, because I would use one half a day, I would jump to another one, etc. And at the end, it's a mishmash, and you don't know. There's no clear scientific finding. Yeah. So I think that's something important, and especially in the context where we're in a bit of pressure as academics to write bigger and bigger grants to get fancier and fancier equipments. I think at the end you can do a lot of extremely good science with not too much resource or labs. Yeah.
That's very wonderful. I want to thank you for mentioning that, because I think that's a very important point. Thank you for mentioning that. I don't know if you have any final words you would like to say. Maybe, yeah, if you have any final words you would like to say.
Well, yeah, I would say again, yeah, go. If you're interested in this area of research, bioinspiration, whether it's for materials or robotics or optics or whichever, then just go out there. And I think the most important thing is to have fun. Go have fun in the lab or on your computer if you computer model, and if you do computer modeling. Just have fun. That's the most important part, I think.
Wonderful. Thanks so much, Professor Francois. I think it was very inspiring. Thank you. Thank you.
Okay, thank you very much.